I think we can get started. So today is the second day of the internal combustion engine course. Let's see if we can move along here. So the goal today is to introduce you to some of the developments in computer modeling of engine processes. Today I'm going to spend some time introducing engine combustion physics and chemistry, the things that really need to be modeled. And then I'll talk about premix charge or spark-ignited engines. Then I'll introduce spray modeling. And we'll talk more about spray modeling when we get to the engine applications tomorrow. So let me start off with a discussion of engine combustion physics and chemistry. OK, so the modes of engine combustion. I did mention several modes last time. For example, we spoke about HCCI. The picture on the left shows a typical image taken at the Engine Research Center for homogeneous charge compression ignition. You notice that the combustion appears and then disappears. That's because combustion is occurring pretty much everywhere in the combustion chamber simultaneously. Let me see if I can get that to show again. Although there is some spatial distribution, but it occurs very quickly. With spark ignition, combustion starts at the spark plug and then spreads out via a propagating flame as it moves away from the spark area. And in diesel combustion on the right, we have injection of fuel. You should see the fuel jets appearing. Show that one more time. Fuel jets appearing, igniting, self-igniting without the need for a spark plug, and then combustion taking place. So HCCI shares the characteristic of diesel combustion that it is auto-ignition. There's no spark plug needed. Spark ignition, on the other hand, requires that you ignite the mixture and rely on flame propagation to finish the combustion process. So to understand these regimes, Professor Kamimoto introduced a plot some years ago that is very, very useful. It comes from essentially modeling the combustion process, starting with a given value of equivalence ratio. That means fuel-air ratio. Stoichiometric is 1 here. And at different temperatures, and calculating after a certain amount of elapsed time representative of an engine operating condition, the amount of various species that you would see in your calculation. So for example, at high temperatures and equivalence ratios in the range below stoichiometric, you'll see a lot of NO or NOx. With high amounts of equivalence of fuel, in other words, high equivalence ratio, you see the formation of soot. At low temperatures, you see unburnt fuel and carbon monoxide. So basically what this plot indicates is if I go to a particular point in a combustion chamber, a location in this picture, for instance, I can identify, OK, here I have a lot of fuel. It's kind of cool. So I'm at low temperature. I have a lot of fuel. So I can expect that I'm going to get soot from this region here. So this plot is very useful because it helps you identify for different types of combustion what to expect. For example, if I have early injection, so injection during the compression stroke, such that the ignition takes place after the fuel and the air has already had a chance to mix, I lower the equivalence ratio, and I produce much less soot. So that's what's called premix charge compression ignition. Homogeneous charge compression ignition, on the other hand, operates at one point. Right? You start the combustion process when you have auto-ignition occurring, say, at a certain temperature. And so the HCCI is operating in this, what we call high-efficiency clean regime, in between the NOx island, the soot island, and the unburnt fuel or CO island. So that's why HCCI is such an interesting combustion strategy. Conventional diesel, on the other hand, covers the whole range. There are going to be places in the combustion chamber where you have rich mixtures that are cool, that lead to soot formation. There'll be regions in the combustion chamber where you have lean mixtures locally and high temperatures that leads to NOx. And so one of the problems with the diesel is that because this operating range covers so much of this plot, you have both soot and NOx to deal with. A spark ignition engine operates at, usually it's stoichiometric, and so it operates kind of on the boundary here where you have essentially low soot and NOx levels compared to what you would find in a diesel. For HCCI, as we discussed last time, this is homogeneous charge compression ignition. You have to typically operate pretty lean. In other words, you're not mixing the fuel with as much air as there is in the combustion chamber. Otherwise, because it all goes off with a bang, you'll have pressure rise rates that are way too high, and you'll damage the engine, or you'll have horrible noise. Partially premixed combustion kind of is an attempt to go somewhere in between conventional diesel and HCCI by allowing enough time for fuel-air mixing by injecting early. So this is a nice kind of summary plot of engine combustion regimes put together by guys at Oak Ridge, where they start off essentially by looking at the fuel reactivity. So a fuel that has low reactivity, such as gasoline, and this is chosen and designed to try to prevent auto-ignition, is what you use in a spark ignition engine. You rely on the spark plug to ignite the charge, this yellow mixture that's pre-mixed, and a flame to propagate through the combustion chamber. On the other hand, with compression ignition direct injection or diesel, here you want to have a fuel that promotes auto-ignition, so a high cetane number fuel. And that's what would be chosen then for a diesel engine. These intermediate regimes shown here are tending towards homogeneous charge compression ignition. Here we have partially premixed combustion, where we not only have premixed gasoline air, but we inject additional gasoline to create stratified mixtures of fuel and air. And the other idea that we'll be talking about later is what we call reactivity-controlled compression ignition, where we introduce gasoline into the intake stream, and then we introduce diesel fuel direct injected into the combustion chamber. So now we have the benefits of not just the low tendency towards auto-ignition of the gasoline, but the high tendency towards auto-ignition of the diesel. And in that way, we can control the combustion process, as I'll discuss with you later. So these are what are called advanced combustion regimes. There are, of course, other concepts, but these are shown here just to point out that fuel reactivity is extremely important. And in fact, it's kind of interesting to go back and look at the history of what's happened in engines over the years. So around 1910, or before 1910, internal combustion engines were used mainly for power generation. And what people found was that those engines basically had what was called spark knock. That means they essentially had HCCI type combustion occurring even though there was a spark plug. So they had a mixture of both spark ignition and then the charge would go off with a bang. And the result was that the compression ratio of those engines was restricted to about 4:1. That's extremely low. So a lot of work was done, particularly at Delco. This is what is, I've forgotten what this stands for, Dayton Electric Light Company, I think, and General Motors, to try to find fuels that would allow higher compression ratio operation, because people knew that to get efficiency, you want high compression ratios. And one of the things they showed fairly early on was that kerosene was knocking or providing uncontrolled combustion much worse than gasoline. And so they thought the reason for this was that kerosene was more volatile than gasoline. And so they explored various concepts. But one of the things that they tried just in the lab out of desperation, I guess, was to add a dye to the kerosene, which was actually iodine. And the reason that they did this was they noticed that here in the East Coast, there's a flower called the Mayflower, which has red leaves. And even though you have snow on this plant during the early spring, it still flowers. And they argued, well, this red color must be absorbing sunlight. And if we add red dye to our kerosene, maybe we can avoid knocking. So they ran this engine with iodine, and they found it worked fantastically. So then they said, well, we've discovered the solution for increased compression ratio. Well, unfortunately, other red dyes didn't work. And so they finally realized it's not the red dye, it's something in the iodine. And they had basically discovered an anti-knock additive. Very interesting SAE paper that describes this history if you're ever interested in looking at it. So in the 20s and the 30s, people then did a tremendous amount of research looking at other additives that they could add to fuels to prevent knocking. And one of the things they discovered was adding an amine was a very successful approach. And in fact, the fuel efficiency that they were able to achieve by having higher compression ratios made possible the first nonstop airplane flight from New York to San Diego in the 1920s. Well, this was kind of important. If you know your history, 1914, 1918 was World War I. These were guys who were flying planes, and their lives depended on it. So having a plane that could fly for this amount of distance was really, really important from a national security point of view. So this essentially inspired General Motors, the US Army, to study hundreds of different additives. And in the process, they found amines and then, of course, tetraethyl lead eventually to allow compression ratios up much higher than the original 4:1, up to maybe 7:1. That gave 40% better fuel efficiency. However, when you ran an engine with these fuels, what you found was that they stunk. In fact, the engine was called the goat, because apparently goats stink. So much research was done to try and find other additives, and finally tetraethyl lead. However, tetraethyl lead, although it was a wonderful knock suppressant, it caused other problems. It led to solid deposits, damaging exhaust valves, spark plugs. And so other additives had to be added to the fuel, bromine, chlorine. And this established a partnership with the Ethel Dow and DuPont companies who found that they could get bromine and chlorine out of the sea. And it was a huge enterprise. It takes 10 tons of seawater to make 1 pound of bromine. But that's how important it was to be able to run with these knock suppressant additives. Also, during World War II, they found special fuels were available or useful. For example, a fuel called tryptane, which was basically isoheptane, allowed the use of compression ratios up to 16:1. This gave them tremendous advantage in the air because of the fuel efficiency. They could fly from Britain to Europe and then back again without any troubles with running out of fuel. Okay, so tetraethyl lead was what was first used in the 20s and so on to help improve the anti-knock characteristic of the fuel. And people worried about lead poisoning. And in fact, in 1926, the US Surgeon General determined that tetraethyl lead posed no health hazard. So tetraethyl lead, has sometimes been called the mistake of the 20th century, was used for 40 years by the industry to help control the anti-knock. In the 50s, Hagen Schmidt showed that the smog in Los Angeles basin was due to hydrocarbons and NO, and cars were a large source of these pollutants. Eugene Howdrey developed a catalytic converter around the same time, which of course all cars have today, but lead was found to poison these catalytic converters. So that was another reason why people wanted to move away from use of tetraethyl lead. 20 years later, in the 70s, the EPA announced that they had discovered that lead was now not good for humans and that gas stations must offer unleaded gasoline. However, leaded gas was still used for aircraft all the way till 2000 in Europe. The point is, and the reason I show these slides is I want to emphasize that it took world wars and national security to develop the auto fuels that we enjoy today. They just didn't happen automatically, okay? There had to be a real reason for it. Today's engines and their fuels would not have been developed if you hadn't have had this close collaboration between the engine original equipment manufacturers, the energy companies, the chemical companies. And a consequence of this is that nothing really is going to happen without a collaboration between big engine, the companies that make the engines, big oil, the companies that make the fuel. And the transformation in our fuel system is just not going to occur very easily. Even though people talk about it, there's a tremendous amount of inertia. So my conclusion from all of this is that a new concept engine must be able to use today's fuels. And the new fuel must also run in existing engines. So we cannot just tomorrow say, oh, I found this great fuel. I'm going to tell all the oil refineries to make it. It's just not going to happen. Eventually, over time, things can change, but I hope we don't need a world war or something like that to make the change happen any faster. So this plot is very interesting from Eric Curtis at Ford. It shows the compression ratio in green here as a function of time. Starting out at 4 for those early engines, the generator engines at Delco, and then eventually increasing when people found how to increase the octane number of the fuel through the amines or the TEL. And you can see that then allowed a big increase in the power out. This is horsepower per liter, going from basically really inefficient engines. And as the research octane number increased, you saw big increases in engine power. In fact, if you look at the time between end of World War II and the early 60s, people really didn't care much about fuel consumption. The only thing they cared about was whether they could speed up that car and drive like crazy. So that whole era there was this big increase in power was the design of the engine, even though the octane number and the fuel type stayed pretty much constant. Although I read somewhere that in California, at a certain time in the 50s and 60s, you could go to a gas station and there would be 15 choices of octane number that you could choose. And if you had a muscle car, obviously you chose the one with the highest octane number. Okay, so then in about 1970, or actually 60, the Clean Air Act came, and in response to the fact that the catalytic converter was now something that people realized was important because of clean air, and that the tetraethyl lead was a concern. So there was a lot of research done on fuels in this period. And then to top it all off, we had the Arab oil crisis in the early 70s, which led people to do even more research in engine combustion. Interesting thing is if you look at what's happened since like the 90s and 2000, there's been a steady increase in compression ratio, even though the RON, or the octane number of the fuel, has stayed pretty constant. And part of this has to do with improvements in the combustion strategy. So here we have gasoline direct injection instead of port fuel injection. So this is now leading to those advanced combustion regimes that we're going to be talking about. So there's been a significant improvement in vehicles over the years that this slide summarizes. Okay, so one of the main questions that people ask about spark ignition engines is, how is it possible for an engine to operate from 100 to 20,000 revs per minute? If I'm, a Formula One racer, I travel at this speed or this engine revolution per minute. If I'm a huge tanker and I'm operating my engine at idle, if I'm a spark ignition engine, I can go over this incredible range of speed. How is that possible? So I know I have my combustion chamber filled with fuel and air. I ignite it with a spark, and a flame propagates. Somehow it can operate over such a wide range of speed, which means the time available for combustion is drastically different. And the answer is because of turbulence. The turbulent flame speed scales with the engine speed. How is this possible? If you look at the kinetic energy of the turbulence in the combustion chamber, it scales as the square of the piston speed. The length scales are essentially determined by the size of the engine, so the piston radius or diameter. The energy dissipation rate you can get by looking at the time scales is then, as this formula shows, and the diffusivity, which is the kinetic energy squared over its dissipation rate, comes out to look like a velocity times a length scale, which, by the way, is almost the same as what you would have got from kinetic theory, except that here this velocity is the speed of molecule movement, and L is the time between collisions. So there's a similarity in the way that quantities are diffused or transported in the argument for turbulence, that the velocity and the length scale are the important parameters. Okay, so this kind of thinking led Professor Bracco, and I was part of his group, to propose a model which we called the characteristic time combustion model that could help explain this. And the idea of the model was the following. If you consider a species in your combustion chamber, maybe fuel, you say that the rate of change of fuel with time, fuel consumption rate, is equal to the difference between the local fuel concentration and its equilibrium value, which in the case of fuel would be 0, right? Divided by a time scale. And this time scale is the turbulent time scale determined from the piston dimensions and the piston velocity. If one uses this to estimate what the fuel conversion rate is, and go back to the simple theory of Maillard and Le Chatelier for propagating flames, and here's a little flame that's propagating out. Maillard and Le Chatelier showed that the turbulent, or the flame speed for a propagating flame is the square root of the diffusivity times the rate of heat release, or in this case, the rate of fuel consumption. And if you plug in the diffusivity and the rate expression shown here, you find that the turbulent flame velocity is proportional to the piston speed. And that agrees with experiments, hence a nice model, right? Called the characteristic time combustion model. Now, at first sight, you say, well, we're all done, right? So spark ignition engines, we can close the chapter. But nowhere here did I say what kind of fuel we were running. And we know that with different fuel, we have different flame speeds. So somehow this model doesn't capture all of the information. And in fact, to this day, we still don't really understand how fuels influence the turbulent flame speed. And I'll talk more about that, obviously, as we move along here. But the basic idea is that without the turbulence, engines would not be able to cover this wide range of operating timescales. Let's look at the diesel engine. Okay, the diesel engine, here's I'm showing one half of a combustion chamber. This is the piston here. Here's the head, and here's a fuel spray injected into the diesel engine. We inject fuel, and at a certain moment, here in this case, injection was 18 degrees before tap dead center. At a certain moment, we start to see ignition. And this plot here shows that the ignition occurred at roughly 8 degrees before tap dead center. So that's an auto-ignition process. There's no spark plug here. Somehow the fuel rearranges itself to ignite and release energy enough to start the combustion process. One of the early models that was available, and to be honest, this model captures most of the physics that we still know today, was called the Shell ignition model, which basically said if I have my fuel, somehow it is oxidized to produce a fuel radical. So you see an increase in fuel radical amount here. This radical breaks down to form what are called intermediate species or labile intermediates, which are shown by this expression here. And those intermediate species react to produce branching agents eventually, which lead to runaway ignition, because for each branching agent, you get 2 radicals. There was one constant that we found could control the ignition time, and that was the time associated with the decay of this labile intermediate. So it was a very simple model, and it worked really well. Okay, so that's how you get ignition. But what happens after ignition? So for the modeling, what we did was we said, okay, well, once we have ignition, let's switch back to the characteristic time combustion model. So the rate of change of, say, fuel with time is driven by the distance that fuel is away from its local equilibrium. The difference now, though, is what's the time scale? The time scale is determined by the injection process. In other words, the size of the injector nozzle and the injection velocity is what sets up the turbulence, and it's this time scale that now controls the combustion process. So that was the basic diesel combustion model that we used for many years. Just to summarize then, turbulent mixing plays a huge role in engine combustion. In the spark ignition engine, you have hot products behind the flame being mixed with cool reactants ahead of the flame, and it's through this process that a flame is developed and propagates into the mixture, the time scale being associated with the turbulence in the engine caused by large-scale motions and the piston velocity. This plot down here shows turbulent flame speed versus the fluctuating velocity, or the square root of the turbulence kinetic energy. You can see that it's kind of a linear relationship. However, there's a lot of scatter around this, and that is where this other normalization parameter, the laminar flame speed, comes in. As we'll see, the laminar flame speed kind of perturbs this nice linear relationship in a very complicated way. For diesel, here's our diesel jets. We inject the fuel. Because of its high momentum in the form of spray droplets, they exchange momentum with the air, entraining the air into the combustion region. Here we set up a diffusion flame. The characteristic mixing time is again associated with the nozzle parameters, the injection nozzle diameter and the injection velocity. So that's very important, and when we talk about engine combustion, to consider turbulence. So, summary. Gasoline engines require spark ignition. The fuel is designed to prevent auto ignition, so we want high octane number fuels. In order to get fast flame propagation, we need turbulence. There's a kind of downside to having turbulence, as you probably know from your heat transfer studies, right? The more turbulence you have, the higher the heat losses. So that's a negative associated with having high turbulence engines. There are issues. We have high temperature behind that propagating flame. The high temperature is required to get the flame to propagate. And then ahead of the flame reaches the wall, it can quench, and that leads to unburned hydrocarbons and CO. Again, the compression ratio and the fuels determine whether you can expect knocking combustion or uncontrolled combustion ahead of the flame. These engines typically require throttling in order to control the combustion process. That means you're going to have pumping losses. And the end result is thermal efficiencies that are around 25%. Now, there are things you can do to increase this, but this is a typical number, a starting point, if you like, depending on the compression ratio. Diesel engines have sprays and diffusion type combustion, or non-premixed combustion. This leads to locally rich mixtures in parts of the combustion domain. Other parts of the domain have high temperatures, which leads to NOx. On the other hand, we can expect higher thermal efficiencies. We don't have throttling. And there are other aspects of the combustion process that lead to improved performance, such as shorter combustion duration. The homogeneous charge and the premixed charge compression ignition is kind of shown here, everything going off with a bang or more or less. Generally are restricted to low temperature combustion because the equivalence ratios are low, so you don't get much heat release. The combustion process, the ignition is chemically controlled, so it depends a lot on the compression ratio. It's very sensitive to the type of fuel, its octane number, for instance. Also, it's difficult to control the combustion process because it's so sensitively dependent on parameters such as the intake temperature, the amount of residual charge, the amount of heat loss due to heat transfer. However, because we're operating in a lean mixture with low temperatures, if you go back to that first Kamimoto plot, you'll see we can operate in a low NOx and soot region. And the heat losses are low, so we can typically see thermal efficiencies around 50%. So I mentioned the fuels. If you just look at this plot here, which is temperature versus crank angle, here's top dead center. during the compression stroke, we compress the mixture. If we're dealing with a fuel like gasoline, that's a single-stage fuel that is hard to ignite, if the compression ratios are appropriate such that you get to a high enough temperature at the end of the motoring compression, you might get ignition. It might occur very quickly, and in that case, you would be looking at HCCI-type combustion. For a fuel like diesel, which is very easy to compress ignite, in other words, at relatively low temperatures, what you see is you compress, and then it's actually a two-stage combustion process where you have some initial heat release, which makes it even worse. Now the temperatures are higher during the rest of the compression until the second stage takes off. And now you have much earlier combustion. So diesel is just not a good fuel for HCCI engine by itself. And we'll talk more about that later. OK, so how do you model all of this? So I'm going to start off by looking at premixed combustion and just a quick review of chemical kinetics. The other lecture series here that go into the chemical kinetics in much more detail than I'm going to do. But basically, the equations of interest are the species and energy conservation equations. So here we have, for species density, for species I, the rate of change with time. We have a convective term. We have a diffusion term. Then the circled one is the term due to combustion. Species I changes because of combustion. Later, we'll see that it also may change because of spray. At the same time, we're solving for the heat release, and we're going to use the energy equation. And there'll be a source term with the heat release from combustion. Tomorrow, we'll talk a little bit about radiative heat transfer, and there's also the spray contribution. But today, we're just talking about the combustion part. So the simplest approach to modeling the combustion process in your computational mesh is to say that in each computational cell, the combustion occurs as though that cell was a well-stirred reactor. So then that really depends on turbulent timescales. Can you really assume that everything in that computational cell is homogeneously mixed? And it turns out to be a surprisingly good assumption, especially if your mesh sizes are reasonable, 1 millimeter type dimension. However, that's also an active area of research. So if one then wants to specify what this combustion source term is, again, I'm looking at the mass fraction of species I changing with time. Here's my law of mass action, basically. My chemical equation for each reaction has the stoichiometric coefficients for the reactants and products. The difference between them times the mass reaction rate summed over all of the reactions involving that species is what I need to solve. The mass reaction rates come from the law of mass action, which is the product of the concentrations of the reactants times the forward reaction rate minus the product of concentrations of the products times the backward reaction rate. And these reaction rates are typically Arrhenius functions with a pre-exponential dependence on temperature and an exponential temperature dependence. The backward rate is often calculated using the equilibrium constant for that reaction, and that's calculated knowing the Gibbs free energy and so on. So I'm not going to go into that in much detail. Once you know the rate of change of species mass fraction, you can multiply by the energy associated with that change and get finally the temperature change due to combustion. So that's just a review. So the chemistry models. So how detailed do you really need to get? Let's just talk about the simplest one that I could find, which is for methane. Involves 15 species and 31 reactions. And here's the even simpler formula. CH4 plus 2 oxygen goes to CO2 and water. If that was the only equation, we would be done. However, it doesn't happen this way. You have to consider at least all of these reactions in order to actually fulfill this overall global step. So if you write down all the reactions, you can see that it starts over here, where somehow the methane is attacked by a catalyst, which comes from the hydrogen-oxygen chain. And in this case, I'm just writing down two of those equations. The hydrogen attacks the methane. It's called the initiation step with H-atom abstraction to produce the methyl radical. Once I have methyl radicals, now they can undergo a set of reactions again through participation of the catalysts here to produce formaldehyde and also methylene. Once I have the formaldehyde, I produce the formyl radicals. And then finally, from the formyl radicals, I get CO. And that takes me back to reaction number 10, which is the one that Professor Dreyer mentioned at lunch today. It's probably the most important reaction in combustion because most of the energy release comes from this reaction right here. But to get there, you have to go through all these steps. And this is for the simplest fuel that there is. Of course, there are other reactions that I haven't discussed here that depend on equivalence ratio. You see different sets during rich combustion versus lean combustion and so on. But this is a prototype of a very simple reaction. So solving this set of equations would be relatively simple because so few species are involved. Let me just talk a little bit about the physics of what goes on during one of these typical reactions. So let's consider methane plus OH going to methyl and water at a rate that's determined by an Arrhenius constant. As I said, the rate of change of methane concentration with time is the product of the rate constant times the product of the concentrations of the reactants. And you can write that as a mass reaction rate term omega sub CH4 divided by the density of the gas mixture and the molecular mass of methane. And you pick numbers from the literature, typical numbers, and you can plot as a function of temperature the course of the reaction. So here's our methane fuel. It's at low temperature, so we start the reaction, and it's consumed by when it reaches about 2,400 Kelvin. Here's the rate constant plotted over here as a function of temperature. And of course, because the product of this K, which is increasing, and the CH4, which is decreasing, and the OH, of course, leads to a mass reaction rate profile that looks like this. We have very little reaction at low temperature. Reactions end when all the fuel is consumed at high temperature, and there's a peak in between. Okay, so it's interesting to try to develop an understanding of equations like this and what determines the ignition for such a simple system. So here are our equations, again, our mass fraction rate of change with time and the corresponding temperature change. It turns out that you can create a model equation with just the parameter u here, which just tracks the temperature. So for instance, when the temperature is equal to the unburnt temperature, this parameter u is 0. When the temperature is the burnt gas temperature, this parameter is equal to 1. So I can plot u going from 0 to 1 over here. And I can cook up a term on the right-hand side of the equation that represents this mass reaction rate, for instance, that has the shape that we saw on the previous slide. Namely, it's 0 initially, it has a maximum, and then goes back to 0 again when we reach the burnt state. And we can find an analytical solution for equations like this in terms of this parameter beta here, which measures the rate of reaction, if you like, and m, the shape of this. And it turns out to be a fairly complicated analytical solution in terms of the hypergeometric function. But we can look at it in this region right here where you start the combustion process. And what you find is that the combustion requires some initial seeding in order to start the combustion process. And this is referred to in the literature as the cold boundary difficulty. Basically, you need something to kick the reaction to get it to start. However, if you assume that you have a certain amount of a temperature increase that may have been caused by turbulent mixing or whatever, you can then determine an ignition delay from this type of solution, and the result is shown over here. The ignition delay depends on the initial value of this ordinary differential equation. But it gives you a feel for what is required to get ignition delay predictions. You do need to have some understanding of what's going to start off the combustion process. If you go to a real fuel, like we did when we spoke about the Shell model, and look at what actually happens in hydrocarbon kinetics, you see something even more complicated, the so-called negative temperature coefficient, where you start with your hydrocarbon fuel, you have H atom abstraction forming a radical. And this radical can go through two paths. One is the so-called olefin path, and the other, the so-called QOOH branching path. So at low temperatures, it turns out this path is favored. And so you'll see the induction period or the reaction delay decreasing as the temperature increases. And at a certain moment, you'll start to see an increase in reaction delay or time of ignition. And that's this negative temperature coefficient phenomenon. And that's caused by now this path to the olefin starting to take preference. So this is what you might think of as a two-stage fuel, right? Where you saw, first you saw some combustion occurring with appropriate heat release, and then it kind of switched off, and then you get again a second combustion process occurring. So the first stage ignition occurs through this branching step here, and that's followed by the second stage ignition, which involves the catalyst species, again, the hydrogen oxygen system to a large extent. I like this chart which Marco Mel put together, which describes HCCI combustion in those terms. Here's the same set of reactions that we discussed before. In this light blue region here is the degenerate branching path, where it involves the aldehydes and ketones that come from rearranging and isomerization steps of the parent fuel. And then you have this orange path where you form the olefins and so on. And notice that here, the heat release, which is being plotted here, actually goes to zero again. And then you have ignition occurring, which gives you the main combustion process, and that's the fast high-temperature combustion involving hydrogen peroxide in particular. Okay, so that's the kind of physics you'd like to see in your combustion model. The problem is that the mechanisms that describe the entire physics that I've just described can become extremely large. For a CFD, it's really not practical to use a mechanism with more than about 100 chemical species. But at the same time, it has to be able to predict order ignition times accurately. Also, you need those reactions in order to look at minor species, which are necessary for pollutant prediction. So if you look here, this is a plot from Professor Law's group some time ago that shows number of reactions versus number of species. They found that if you look at the mechanisms in the literature, you typically have 5 times as many reactions as you have species. Our little methane reaction is down here. But if people are looking now at fuels with way more species than I'm showing over here, there's a real problem. I mean, here we're only up to C9. We want fuels that have C20 and higher. And so the number of species has just become inordinately large to be able to implement a detailed reaction scheme in a CFD calculation. So that's led to the idea of mechanism reduction. And at the Engine Research Center, my colleague Youngchul Ra spent a lot of his time looking at reduced mechanisms, and we use them now in our engine combustion simulations. So for example, for the primary reference fuels, that's a mixture of N-heptane and isooctane, he has developed a mechanism which we call the ERC-PRF mechanism with 41 species, 158 reactions. That came from the Los Alamos National Lab, 500 species N-heptane mechanism, 800 species isooctane mechanism, and an earlier N-heptane mechanism of ours. And this just shows its performance. Now I'm plotting ignition delay time versus 1 over temperature, so the plot's kind of reversed to what I showed you earlier. But it shows that as you go from low temperatures to higher temperatures, you start to see the negative temperature coefficient showing up with N-heptane here. This is for N-heptane air at 1 stoichiometric and 40 bar. This plot here shows the same thing except for isooctane. If you can see the scales, this goes from 0.01 to 100 log scale. This is 0.01 to 10. So it immediately shows you that isooctane is much less reactive than N-heptane, and that's captured by the models. And here you see blends of them. So here we have the isooctane, down here we have the N-heptane for these conditions, and then different blends of the PRF fuels. And it does a reasonable job of predicting the ignition delay. So then we got more interested in real fuels. And if you look at what fuels are made of, what the constituent species are in practical fuels, you find there are hundreds of them. And so we decided to produce what we call surrogates, where the physical properties of the fuel are accounted for by including a list of representative species. For example, the cycloalkanes in the fuel we treat using cyclohexane, a decalin. The N-alkanes we might with endodecane or N-octadecane. The isoalkanes, again, treated with certain surrogate species and aromatics. So that's for the physical properties, and we can get those from databases that give you the density, the viscosity, and all the parameters associated with those fuels. And then the chemistry surrogates for each of those classes, we picked from the available Los Alamos National Lab detailed mechanisms, but species that we felt represented those classes of surrogates. So cyclohexane for the cycloalkanes, N-heptane, and isooctane for the N and isoalkanes. For the larger molecules, N-tetradecane and toluene for the aromatics. If you look at the Los Alamos available mechanisms on their website, you see the huge number of species associated with each of these classes of fuels. We reduced those mechanisms. His paper here describes the methods used, and eventually came up with what we call the Multicam mechanism, which is basically 100 species, 350 roughly reactions that can handle this wide class of component surrogate species in a real fuel. And this just shows some of the performance in one of his papers here. This is for 8 surrogate fuels with N-heptane, isooctane, tetradecane, cyclohexane, toluene, decalin, and ethanol, and the butanoate for biofuels. Propane, N-heptane, isooctane, toluene, methyl cyclohexane, decalin. Again, experiments from the literature shown in the boxes here. And you can see that this Multicam mechanism does a reasonable job for a wide variety of fuels. Okay, so having determined what we're going to use for our chemistry, we've got a mechanism that allows us to predict ignition delays reasonably well. We now want to put that into our CFD code. And so, for instance, in the species equation, we need to introduce the source term for combustion and also in the energy equation. If we're going to do that for every computational cell in the computational domain, we're adding a tremendous amount of computing, right? Because even in one cell, if you have lots of species, there's a lot of time devoted to solving the chemistry. And now we've got many computational cells, so that's a concern. So that's led to a lot of research in my group on improved solver numerics. And in particular, Federico Perini has written a code which is available on our website called SpeedChem, which has the advantage that its computer time increases linearly with the number of species. So that's actually a major accomplishment because earlier chemistry solution techniques did not have that type of scaling. His approach is to basically evaluate the functions and equations in matrix form. So here's the form of the Jacobian matrix. And then essentially to solve this Jacobian, recognizing that it's a sparse matrix. If you only have 47 species, then it's not very sparse. But by the time you get to larger number of species, the matrix, if you look at its elements, is really sparse. And we make use of that sparsity to increase the solutions. For example, the evaluation of the functions, the development of the Jacobian, and then finally the linear system solution. And try to keep that as linear as possible. Now, this is sort of the range of interest for us in terms of the Multicam mechanism of 100 species. And you can see that we can keep the computational time down to reasonable numbers and yet still solve fairly practical problems. The other approach that we use quite routinely, depending on what type of combustion we're looking at, is what we call cell clustering. So you've got all these computational cells with fuel and air in those cells. Turns out that some cells look very much like other cells that may be neighbors or may be situated remotely from that particular cell. And if we, instead of solving them separately, group them together in this adaptive mechanism clustering scheme, so we can grab cells from here, which have very similar temperatures and equivalence ratios and so on, solve them just once, and then remap back to get the solution, and then remap the solution back to the original domain, we can save a tremendous amount of computer time. And then if we go even further and say, implement the extended dynamic adaptive chemistry scheme, which says, okay, why am I tracking some species that were only important during ignition, and I'm already in the second stage of combustion? Let's throw away those reactions. So you now reduce the mechanism size depending on the combustion history. So you can get huge savings in computer time by doing this. For example, using the ERC PRF mechanism, looking at HCCI combustion here. This is cylinder pressure versus crank angle. Experiment is shown by the black line. The simulation using full chemistry took 48 hours, 2 days. Using the adaptive mechanism approach, brought that down by an order of magnitude, and then additional 50% reduction with the elimination of unnecessary reactions. So this allows you then to look at a problem that used to take 2 days in 2 hours. So you can actually study a lot of combustion variables with this type of speed up. So just to finish up on this topic, I mentioned the reason we're interested in detailed chemistry has to do with our interest also in pollutants. So for instance, if you look at the EPA standards, they include not just particulate matter and nitric oxides, but other species. And in particular, the mobile source air toxics rule identifies species such as benzene, butadiene, formaldehyde, acrolein, acetaldehyde, and so on, as species that need to be controlled, hazardous pollutants. So one would like to be able to predict how much of this you find in your engine exhaust, which means you need to include these species in your simulation. So that's why we do need to have a fairly detailed mechanism that will actually allow you to track these species. There are others down here that I've listed as well. Most of these we try to include in our chemistry mechanisms. Bottom line, though, is for the industry itself, the target is unburned hydrocarbons and nitric oxide leaving the engine exhaust. And the targets you can see here have been reduced from back in 1965 to now, the LEV 3, by 99.8%. That's a huge reduction in emissions. And how is this done? Well, the catalytic converter is a big part of this. It also has to do with very specialized treatments in cold start before the catalyst has a chance to heat up You want to make sure that the engine is operated in such a way as to minimize HC plus NOx, because a lot of it comes from just the first minute or so of starting the engine. So that's where research really plays a major role in terms of the engine system itself. And just finally, I forgot to mention earlier, we also have models for nitric oxide, basically starting from the extended Zeldovich steps. We also have a model that includes thermal NOx and prompt NOx, and actually some connections with cyanide as well on the rich side, where you can have interactions between NOx and soot. And there's some papers in the literature that describe this that you might find interesting. So to summarize, internal combustion engine combustion physics depends crucially on the fuel chemistry. The octane number basically is what allowed us to go from compression ratio of 4 to compression ratio of 16 today, or 12 certainly in production. And that led to a tremendous increase in fuel efficiency. Much progress has been made in understanding and modeling the chemistry of realistic fuels. The various combustion regimes require different fuels, right? We saw the auto-ignition characteristics play a major role. And then finally, meeting toxic emissions regulations will require even more research in advanced engine research. And here are the references. So we can take a couple of questions.
That reduce the thermodynamically similar cells to reduce computation time? Can you clarify that?
Sure. So here's my computational domain. Here's just a piece of the piston. I'll show you part of the piston here on the computational domain. If I look at the composition of the fuel, oxidizer, and all the other species in this cell, and I find that they're very similar to what I see in that cell over there. Why solve for each of these cells separately? I combine the two, do one calculation, and then feed back the results to each of the individual cells. So that's this adaptive mechanism clustering. The other approach is then to say, well, I'm at this point in the combustion process where these reactions are just not important anymore, I'm not going to even bother to solve it. So that's where the speed is. Yeah.
It's always useful to use a simulation because it's cheaper compared to the experiment. Is there any threshold for us to switch from using 1D simulation into 3D simulation? Like if there's certain compression ratio or something?
That's a good question. So I showed you, I hope, yesterday that to use the 0D or 1D models requires calibration against something. Yes. So if you have an experiment, great, use that. But if you don't have an experiment, or you're looking at a new combustion strategy that you've never seen whether it operates or not, you do need to use simulation tools. And in fact, I'll show you tomorrow an example of where we use computer optimization to discover a new combustion regime. That when I told the guys in the lab, hey, try this out, they said, oh, we're not going to do that, it's going to blow up the lab. I said, please. And they tried it, and look. So that came from modeling.
I have a question. So, I have a graph for the reaction candidate for like biofuel and biofuel, which is more complex. This is in the mixture.
Yeah, so, and they're large molecules. But we have reduced mechanisms also for the biofuels, the various polyates, and I refer to some of them in the references there. You can take a look at them. That's, again, a lot of work has been done in producing some of these reduced mechanisms. Just a quarter space. Okay.
In one of the opening graphs, you showed that not much progress has been made against the cavity in terms of the octane number. Why has the octane number plateaued?
Why, for all those many years?
Yeah.
Talk to the people in the refinery. You know, it's very expensive to make higher octane fuel, and it's an economic thing. And also, the engines worked, so there's a trade-off.
1 unit of octane number change costs several $1 million in terms of refinery for 100,000 barrels of gasoline. So it's a very economically sensitive number. So when refineries blend today, they try to control a number of streams that they're going to blend finally to make the appropriate octane number for gasoline. They try to control that better than 1/10 of the number. You cannot measure 1/10 of the number, but they can reproduce the chemical results in terms of analysis that resulted in 1/10 of the number change. It's an amazing ability to control that.
Okay. Was there another question?
With respect to your mechanism reduction, so all these reductions are based on like 0D and 1D validations, right? What is your viewpoint on this applicability to 3D simulation, where we have a complex environment, turbulence, interaction?
So that's a good question. So remember I mentioned the assumption is the well-stirred reactor. So everything in the computational cell is assumed to be uniform. And you can use a 0D model to reproduce experimental data, shock tubes, or the rapid compression machine. Turbulence chemistry interaction is a field of research that's ongoing. I'm going to discuss that to some extent tomorrow in some detail, so let's hold on till then. Yeah.
So I have a question for you about your reduction issues. Whenever we take a detailed model and we're attempting to reduce the dimensionality, we have to choose the targets that we wish to reproduce. And if the targets is heat release, that's an issue. If the target's ignition delay, that's an issue. Those are the targets we would try to optimize in terms of that dimensionality. But then if I start to add other targets, like I want to optimize the targets such that I reproduce the emissions of the engine, I'm wondering if you tried to do that, and if you did that, how successful you were at it. Because now I'm starting to overlay more and more detail requirement in the model. And so we get the reduction that still has high fidelity for those, maybe not accuracy, but high fidelity, becomes more and more difficult.
Absolutely, and that's an area that we really have not made a lot of progress in. I mean, the industry is interested in hydrocarbons and NOx.
Yeah.
They don't go beyond that in terms of regulation. Now, as the EPA starts to say, well, which species are those aldehydes, or what are they in terms of hydrocarbon, then you have to worry about it. And right now we do predict it. We have some results that look reasonable, but it's not been something we've studied.
So I'm glad that Rolf answered that, because I didn't want you to feel like everything is done.
Oh, absolutely.
It's
not.
definitely not done. And the more we try to refine the specifics, the more difficult it gets. And yet those specifics are very important to questions. Here, Rolf was also talking mainly about the combustion event itself. I don't know whether you follow the chemistry during the expansion.
Oh, yeah.
That turns out to be very important. More so in gas turbines than it is in spark ignition engines, where the decompression is a little faster, especially at high speed. There's more chemistry that occurs in terms of the emission chemistry during the expansion. And so if someone's just modeling just the compression and power stroke, it isn't enough to produce emission control.
Okay, maybe we'll take a 10-minute break.